In this last section of this tutorial, we'll talk about some real-time monitoring schemes that have been implemented around the world for the assessment of frequency stability. An online frequency deviation estimation tool was developed and implemented in the Nordic system. It was based on a pretty simple linear regression that looked at past events and took their maximum frequency deviation and the ratio of the contingency size and the system inertia. They found some fairly linear correlations here for under frequency events and then another set here for over frequency events. So they implemented this estimation tool in SCADA EMS, and it calculates the maximum frequency deviation in real time based on the maximum generation contingency or in-feed loss. And while this estimate is acknowledged to be fairly limited, and particularly the assumption that there's a linear relationship between contingency size, inertia, and frequency is probably not correct. The results are reported in the months after it was made operational in June 27 were fairly encouraging. ERCOT developed a reserve sufficiency tool, which is an online situation awareness tool to allow operators to track PFR reserves and other frequency responsive capacity and verify that it's sufficient for current system conditions, for example, the current inertia. And one of the reasons why they built this was because they actually provisioned the reserve responsive reserve requirements sort of 1 year ahead based on historical inertia values, and on the day those inertia values could change, and so they use this tool to ensure that they've got enough, and if they need to provision more, then they shall. Finally, in this, we've developed a real-time frequency stability tool, the RTFS, which is an online situational awareness tool for the control room, and it's used for the monitoring and predicting of frequency stability in real time. So the tool is based on an SFR model with SCADA data providing real-time inputs. So things like system load, inertia, largest generator contingency, etc. So this is the block diagram of the RTFS tool, and you can see that there are some really familiar elements of the SFR models in there. So you've got the inertia block here, and you've got some SCADA inputs for system load as well as the generator inertia to provide a load inertia estimate, and then finally a total inertia estimate. And you have also the PFR model, which is basically a droop feedback model similar to that of the Anderson model, but with each generator represented individually with its own parameters. And then we have from the data, from the SCADA data, we have the breaker status, the operating status, and the outputs of each generator. So the RTFS tool was first deployed for use in the Swiss control room last year in September, and the tool raises an audible and a visual alarm every time it predicts that the frequency stability limits are breached, and in our case it's when the frequency nadir has reached the false threshold, 48.75 Hz. The tool also has a test mode that allows the controller to test the frequency response of hypothetical generator redispatch scenarios. So if you've got an alarm and you needed to resolve that frequency stability risk, you may want to redispatch generators. You may want to dispatch a new generator or change the outputs of existing generators, and the test mode allows the controller to basically try out different scenarios and see if that would resolve the frequency stability risk. So here are some validation plots, so simulated versus actual frequency from two actual generation contingencies, and they show fairly good alignment. So here's one in from February 2020 when we had a 244 megawatt loss, and here's another one from last year in November with a 175 megawatt generator trip, and the blue line in each case is the RTFS tool, and the red line is the actual frequency. We can see here that the tool is always a little bit conservative, which is a good thing because these are actually predictions, so they're not fitted traces post-event, but these are what we would have seen before the event happened. And you can see some pretty good alignment. And we've been pretty confident with the results from the tool thus far.